Hello, everybody. How's it going again? Good to, I guess I'm not seeing you all or hearing you at the moment, but good to be here. Let me go ahead and I should just start with this enlarged. I don't know why I don't. It's very silly. So I want to talk a little bit about ROP and return-oriented programming, but I got to do it slowly because it's a concept that people really struggle with just in general. And that's not because they're stupid or because they don't get it. It's just a lot of information and you have to think about it in a very specific way. And if you haven't done reverse engineering before or any kind of exploit development or vulnerability hunting or vulnerability research, as it's appropriately called, then you're kind of in a tough spot because, let me say that a different way. You might get discouraged early on, and you should not be. You're not in a tough spot in the sense that anyone can learn it. If you've ever done any kind of programming, you can learn it, and it's all fine. But it's very different from what most people do in their day-to-day life. And so I thought I should do some videos on it. I was recently, for reasons I won't go into because they're boring, I decided to redo the I'm not going to say the name. I decided to redo a very popular website's ROP challenges. And I thought, I should change the names of those challenges and do them on my YouTube channel because other people might find it valuable, even if they're not trying to solve. So let me say it. Let me take a step back. I feel like maybe people's ears might have pricked up at the wrong part there. So the challenges I'm talking about, there's no reward for them. You don't get any benefit to doing them. They are strictly for learning. But I don't want to be the guy who posts very obvious spoilers for them on the internet. So I've downloaded them, I've changed the name, and I'm going to do them here on the x86-64 architecture, starting from challenge 1 all the way to the last one. Because I think people would find it valuable just to learn more about ROP, not because I want to give away the answers. So if you happen to find what this challenge is, again, it's publicly available, it's free, and there's no prizes. Don't just copy my answers because you should learn how to do it yourself. I'm just kind of here to help explain what's going on. The challenges are just kind of there to help you put into practice what you know. Anyway, so enough philosophical ranting here. Let me go ahead and get started. So I've got a flag here. Actually, one second. I'm going to edit this out. I should change the flag because the flag will give away what the what the challenge is. Okay, that didn't take very long. So now we have a flag here, which says, you are currently watching Stack's YouTube channel. Now, how great is that? So the description for this challenge is, find a function that looks interesting and try to overwrite the return address of the main function and set it to the address of that interesting function. So one of the things we can do here is look for strings in this ROP challenge binary. This is the binary. I guess I should give a little information about it. ELF 64-bit, x86 64, everything we expect on our current system. So it will run. Let me go ahead and run it. It says, oh shoot. Can I black that out? I will. Okay. Basically what it says is, I'm going to try to fit 56 bytes into 32 bytes of stack buffer. What could possibly go wrong? And then we type something in and we get a thank you exiting. But if we type something more interesting in, maybe we get something more interesting. So it says 56 bytes of user input into 32 bytes of stack buffer. That immediately tells us that at 32 bytes, we will be overflowing. We have an additional, whatever 56 minus 32 is, I guess 24 bytes we can work with. We don't need that many bytes, but let's just think about this for a second. So we'll be overwriting 32 bytes, and we want to get something more interesting than the thank you, we're exiting message that we got here. So let's look at this a little bit more now. So if we run strings on this, we can see, I can scroll here, thankfully, because I'm using Alacrity and not ST, though I love ST. It is hard to scroll there. We see this here, this bin cat flag.txt, and this is very clearly also we see above it, well done, here's your flag. This is very clearly what we want to hit. And I'm not going to do a lot of RE this time around. We'll do that next time. I'm just going to use NM which is a program that's it's on most Linux distributions. Probably not anything BusyBox, but most Linux distributions. And it is a list symbols from object files. I literally don't know what it stands for. I am not sure, but it does this basically, where it lists, again, the symbols that are actually found in the binary. And this will include functions that we might care about. We can also use readelf to do this, actually, because we're using an elf binary, and this works on non-x86 architectures as well. So if I do, what is this, attack, I'm doing this from memory, attack S for symbols. Yeah, so if we do it like that, it's actually a little bit more greppable, because we can grep case insensitive for func, and we'll get the functions that are found as symbols. And what we care about here is this symbol here, ret to win, because it looks interesting to us. So this is an interesting name for a symbol. And what we know about this binary based on, again, I'm not going to do RE this time. This is just basic ROP. But let's assume we've done some RE on this before, and we know that this is a position-independent executable that doesn't use ASLR. Then we'll know this address is going to matter to us. I'm sorry, a non-position independent executable that doesn't have ASLR enabled. So we know this address will remain constant throughout execution. And so if we want to hit this function, what we want to do is somehow get this address overwritten onto the return address of the stack. So let's go back to actually running the man, I'm making this hard. I'm going to have to edit all this out and just to hide a free challenge. Gosh. If we run it again, we see, well, maybe I should just read what it says. I shouldn't show you guys. I'll edit all that out. Let's just assume we know. So what's happening is there is an input buffer for 32 bytes, but the read call that's happening is on this binary is happening for 56 bytes. What that means is anything past 32 bytes we can still write, but it will be outside the stack buffer that's been allocated to what we've been able to write. So anything past 32 will go somewhere else, right? Now again, I'm not just trying to do some, well, let me go back, sorry. Let me go ahead and save this because I haven't saved it yet. We care about this address here. And we care about all of these bytes, because you'll notice a lot of leading zeros, because we're doing x86-64. If we were doing something smaller like MIPS or ARM, we would only care about 8 bytes. I'm sorry, 4 bytes. But right now we care about 8 here. So let's go ahead. Let's save that to something. Doesn't matter what it is. Actually, I want to change that. There we go. Okay, so we know when we add 32 bytes, we will overwrite something. So let's go ahead and try, let's use Python here. Pipe in a command, we'll do print. We'll do A's, because that's the standard, but it doesn't really make a difference. You know, you can do whatever you want. And let's do X's. Okay, so that prints out 32 A's and then 4 X's. Now let's pipe that into our ROP challenge. Okay, so we see the exiting call that we expect there, right? So adding 36 of something doesn't help. Let's try adding 4 more. Okay, so we got an illegal instruction, core dumped. That's good. Well, not good, but it means that we are actually overwriting something that matters. So basically what's happened here is we have 32 bytes, which are taken up by all the A's that we've overwritten, but then there's something past that, apparently 8 bytes past that, like the additional 4 A's we've added and the 4 X's, that does not seem to make a difference. And if we add 4 more, we get the segmentation fault, which is kind of what we're looking for, because that means we've basically what a segmentation fault means is we have touched memory we were not supposed to touch. We've written onto something we were not supposed to write onto. And that could be a potential vulnerability. In this case it is, because this challenge has been designed to be that way. So one way to test this, again, I will talk about tools later, this is all just quick and dirty, is we can use D message, tac T. We'll grep for ROP. Put in a little bit of a password there. So what we see here is we see 58s are V's, right? So if I were to do, let me move this back down to 36. Oh, I didn't overwrite it. I knew that. Sorry. Let me try it a different way. Let me change these to A's as well. So now these are 41s. This is the instruction pointer, by the way, here, this IP. So these are 41s, which is the address that we're hitting. And that's because what I've done is I have made this here after the offset of 40 bytes, A. A in hex is 41. If I change it to B, that will be 42. Right? So we found where we can overwrite the return address. Now, why is it not exactly 32 bytes? Well, the reason for that is because there's some 8 bytes in between the 32 bytes that we expect we can write, and then the 40 that is, I don't know what it is. It might be a good exercise to look into, but it's something. Those 8 bytes are something. So once we get past that something, maybe it's a canary that's inactive or something. That wouldn't make sense because it wouldn't be a canary if it was inactive. Anyway, it's something that's 8 bytes. We overwrite it. All of a sudden, we are now hitting the return address of the function. So what that means is we can now, basically whatever we put in here will control what the return address is based on what we the program we're running. So let's go ahead and look at that address again. This is, again, I won't go into RE tools now, so just believe me when I say this is a big endian binary. And what that means is whenever we write our shellcode or our address in shellcode, we will have to do it in the reverse byte order here. Bytes are basically 2 digits of what you would normally call integers. So like this is a byte 56, this is a byte 07, 40, etc. We have to write it in the reverse order because we're working on a big endian system. So let's start doing, so again, this 56 is the same 56 here, right? Trying to make this as clear as possible because I didn't understand big endian when I first saw it. Oh my goodness. That 07 here is the 07 here. And then the 40 here is the 40 here. And then everything else is zeros. And we want to get to, because we're on an x86-64 system, we want to get up to 8 bytes. So let's, we're on 4, 5, 6, 7, 8. So what do you think will happen here? Well, what will happen is we'll overwrite the offset with A's. And then here we know we're overwriting the instruction, the return address. And the return address is going to be the address of what we found to be the ret to win function. So I call that. And you see we still got a segmentation fault, but we also printed out our flag.txt, which is the file found here. Right? And we were able to do that because we put in here the address of the ret to win function. Like I said before, I won't go into a lot of detail on how the RE of this is done until a couple of videos later, but just pretend you know this already. The bin cat flag.txt is what's called in the ret to win function. So us writing this shellcode here, overwriting the return address with the address of the ret to win function, called this system command, and it even called printing this to standard out, as you can see here. Normally we didn't get that, and that's how we get our flag. So basically what return-oriented programming is, and this is a very basic example, is you want to, in some cases, either use return address that is you control, or you want to use what are called return-oriented programming or ROP gadgets that that all end with a return call that let you call different parts of the program to do whatever you want. And I'll get more into that later. If that sounds confusing, that's okay. But let's just one more time really quickly make sure we go over this. So if I were to change this at all, let's change this to 3. 3. It won't work, right? We got nothing. And the reason for that is because what I've written here is the big endian version of the address of a function in the program, ROP chal1, that calls bin cat, which exists on our system, right? It's calling this from our system back to the 40. There you go. So that's a basic introduction. Idea is, of course, we're overwriting, return addresses, which we'll do more of here in the near future. But just wanted to kind of demystify this on a very upfront level if I could. If this made you more confused, I apologize. Watch the next couple of videos on this, and it will hopefully make more sense. That's it. Thanks.